Alright gang, here we go. This is for Chem 2 Unit 8. We're talking about factors that affect solubility. Should be a lot of fun. Maybe it'll answer some questions that have been burning away in your brains for the last little while about solubility. Who knows? Okay, so we're going to focus on three different ones: solute-solvent interactions, okay, which we briefly touched on in the last video, pressure, and temperature. All right, so solute-solvent interactions. Essentially, it comes down to this phrase, like dissolves like. And this phrase is like all over the place in chemistry land. Okay, like dissolves like. Now, when we talk about like dissolves like, essentially we're talking about polarity. Okay, so if our solvent is polar and our solute is polar, then more than likely it's going to dissolve. Okay, if the solvent is nonpolar and the solute is nonpolar, then most likely they'll dissolve. All right, but if they're opposites, if one is polar and one is nonpolar, then more than likely they do not dissolve. Okay, they don't mix. Okay, so like dissolves like. All right, but it doesn't explain everything. Okay. And we'll talk about some of those exceptions as we move forward here. The stronger the solute, the solvent interaction, the greater the solubility of the solute in that solvent. Okay, so like here we've got nitrogen, oxygen, argon, and krypton. All of these guys only have dispersion forces. Remember, our dispersion forces increase as we increase molar mass, and so we've got these increasing molar masses as we go this way. These are non-polar, right? And so they're not very soluble in water, and we can see this here. They only dissolve in 0.00069 moles of nitrogen per liter of water. So that's not very much. That's not very much at all. Okay. So anyway, but we can see that as the dispersion forces increase, that means that those attractive forces, those intermolecular forces between the solute and the solvent, the solubility increases. So we can see that here it's several times higher solubility of krypton in that water than the nitrogen was. Okay, and it's all because of that increased number of dispersion forces. All right. Now, organic molecules in water, the solubility of organic molecules is an interesting point because our bodies are mostly water, but but they also have lots of organic compounds. We put organic compounds in our bodies all the time. We need to be able to tell whether or not things are going to dissolve in water. And then if you move on to organic chemistry, then obviously you'll spend a full year, 2 semesters talking about organic molecules. And one of the big things is whether or not they dissolve in water. Okay, so the more polar the organic molecule is, the better it will dissolve in water. All right, but there are nonpolar organic solvents that you use all the time. Okay, so the nonpolar organic molecules will dissolve in the nonpolar organic solvents. All right, and so it's kind of this balancing act of which one are you going to use, et cetera, et cetera. All right, so if you have more, essentially one big thing that you can look for is these alcohol groups, these OH groups. Remember we talked about these when we talked about naming organic molecules. So we've got it's cyclohexane here. Okay, it's a 6-carbon ring. Okay, it's got only hydrogen, so this only has dispersion forces. It's essentially insoluble. Then none of this will dissolve in water. Okay, but glucose has tons. It's got 5 different alcohol groups on it. 1, 2, 3, 4, 5. So that's 5 places where you can have hydrogen bonding. And water is a hydrogen bonding monster, and so you can get lots of this hydrogen bonding interaction between the two of them. And so sugar, glucose, dissolves really easily in water, right? And you know this if you've ever made Kool-Aid. Dump that Kool-Aid in, and that dissolves in water right away. And it's all because of these hydrogen bonds. Even though these sugar molecules has a ton of carbons, just like the cyclohexane, it's all about these alcohol groups. Okay, and so here, you've got also the 2 ethanol molecules have a hydrogen bond, and then you can also see that ethanol would also form hydrogen bonds between the water molecules. All right. So the more alcohol groups you have, the more polar it is, and so therefore the more hydrogen bond it has, then the better it will dissolve in water. If you have something that's got a really long carbon chain on it, okay, like a hexane, just 1, 2, 3, 4, 5, 6, and then even if it's a hexanol, this is still not going to dissolve nearly as well as ethanol will, because this whole area over here is non-polar. Okay, it's only this side right here that can have those hydrogen bonds. Okay, so it's kind of a balancing act, and as you do more of these, you kind of get better, more used to it. All right, so a couple of new terms here: liquids that mix in all proportions. So it doesn't. So this is assuming that you have two liquids mixing. So lots of people get this confused as if you're starting with solids, but it's only liquids in your mixing. They are called miscible. Okay, miscible is solutions that are liquids that mix in all proportions. Liquids that do not mix in one another are called immiscible. Okay, so here a hexane and water is immiscible, this hexane in this water, because they do not mix, because the hexane is nonpolar and the water is polar. Now, one thing to take note is notice that the hexane is on top and the water is on bottom, and it's all because of density. Water has these tremendous hydrogen bonds, right? And so it pulls itself in very, very tight. So the density of water is a lot higher than hexanes. So this is kind of an interesting thing. When you take organic chemistry in the future, this is something that's going to come back to haunt you over and over again. Oh, wait, in the lab, you're going to be like, okay, wait, is the organic compound on the top or the bottom? It's almost always on the top. Spoiler alert. Okay. Here we go. So arrange the following substances in order of increasing solubility in water. All right, so we're going to go A, B, C, D. Arrange them in increasing solubility. So we've got hexane here, hexanol. Ooh, we got a diol here, two alcohols on this hexane. And then you've got this chlorine group, chlorohexane. Right. So obviously the plain hexane is going to be the weakest, right? Because it's only got dispersion forces. This guy and this guy both have hydrogen bonds, but this one does not. Okay, but it is slightly polar on this end, so it's got to be more soluble than the hexane, so we'll put it there. So it'll be A and then D, and then so now we're competing between B and C. Well, B has one alcohol group, C has two, so B has to be next, and then the last one would have to be the C. So there you go, mission accomplished. Okay, solubility and biological importance. Okay, so you got fat-soluble vitamins, and there's several of them. So one example is vitamin A. These are non-polar. So here's a vitamin A. Notice it's got this big old chunk of just carbon and hydrogens out here. This is essentially non-polar. It's got this little alcohol group right here. All right. And so it's essentially non-polar. So it doesn't really dissolve in your and the water that's in your body, and because of that, your kidneys can't really filter it out, because your kidneys filter things based off of their solubility, or based off of water, right? So, and because vitamin A won't dissolve in water, is immiscible in water, your kidneys can't really get rid of it, and so it gets stored in your fat tissues. So really, you don't need to take vitamin A supplements, and if you take enough vitamin A, you can actually get vitamin A poisoning. All right, so there's just too much vitamin A in your body. And then I'm not sure if it's deadly or anything. It's like, I'm not really a doctor or anything, but I do know that it's not good. All right, but water-soluble vitamins like vitamin C and these other ones that have lots of these alcohol groups on them, they're very water-soluble. Okay, and so you actually, and these, you take a bunch of extra vitamin C if you think you're going to get a cold, jury's out as to whether or not that actually works. But anyway, if you take a bunch of vitamin C because you think you're getting a cold, if you overdose on vitamin C, it's not such a big deal, because your body can just pee it out, because, it's soluble in your urine, right? Whereas vitamin A, no such luck. Okay. Next effect here is pressure effects. Okay, solubility of liquids and gases or solids do not get affected by pressure. All right, or at least appreciably affected by pressure. So, like if you have a bunch of sodium chloride and you're trying to get it to dissolve in water, increasing the pressure is not going to help it dissolve more. Okay. However, gas is affected by pressure, and we measure this by this Henry's law. Okay, and so as Henry's law says, that the solubility of a gas is proportional to the partial pressure of the gas above the solution. All right, so we get this formula here. We got solubility of a gas is equal to this K value. This K value, okay, is Henry's constant. All right, Henry's law constant is really what it's called. Henry's law constant. Okay, now it's different. Okay, different for each gas. Okay, it's different for each gas, and it's different at different temperatures. Okay, So you got to be careful because, you know, if you change temperatures, your Henry's law constant changes. So you got to watch out for that kind of thing. All right. So essentially what we're saying is if we have this, you know, we've got this piston set up and it's at dynamic equilibrium, we're having we're having dissolving and undissolving, right? Falling out of solution, really crystallization, occurring at the same rate, okay? And we've reached equilibrium. Both these are occurring at equal rate. If we increase the pressure, then that means these guys up above are going to be dissolving quicker, okay? So the rate of the dissolving is going to increase until you get enough in the solution down below where the rate of it falling out of solution matches the rate of it falling into solution or dissolving. And then you reach dynamic equilibrium again. And notice that down here we had 3 blue balls that were able to dissolve, and then over here now we've got 6. All right, so our solubility increased because we increased pressure. So that's just a way of visualizing what's going on. Notice that we had on this right side we've got our solubility in millimolarities, okay, and then partial pressure down here, atmospheres. And notice that, you know, some of these are much more affected by increasing pressure, okay, and there's maybe some patterns to witness there, so on and so forth. Okay, so one thing to keep in mind is, so if we've all had, you know, a bottle of soda, right? And you take that, you know, that bottle, that 20-ounce bottle or whatever, and you first pop it open, and it goes when that gas escapes. Part of the process of making soda, carbonating soda, is that you are going to fill that bottle full of carbon dioxide gas right above it at really high pressure. And because you've increased the partial pressure of the carbon dioxide gas above the solution, much more carbon dioxide gas is going to dissolve in the soda. Right, and then now that more soda or carbon dioxide is dissolved in the soda, okay, it then makes it more fizzy. So that's why, really, like, so you and then they screw on, or they, you know, put the caps on and all that jazz. And then when you take the cap off, it gets, you know, the gas escapes, and you can actually see, like, if you watch carefully the next time, or maybe you've already noticed it, when you open the bottle of the soda, you actually see the gas escaping on its own. Okay, or, you know, you see an initial rush of bubbles escaping just right from the get-go, and that's some of the gas that was dissolved in the liquid that just kind of pops out right away, and then the rest of it will continue to pop out of the gas as you let it just kind of sit, right, and then eventually your pop goes flat. All right. Temperature also affects the solubility of our gas here, okay? And so for most solids, when we increase temperature, the solubility increases. However, this doesn't really work for everything, and then so there's some of them that are actually opposite, and some of them it doesn't really affect it very much. So, like, for example, here we got solubility in grams of salt in 100 grams of water, and this is the temperature. So notice that for, like, potassium nitrate, you know, it's at 0 degrees Celsius, it's at about, like, what is that, like a 13 or so, and then as we increase temperature, it goes up exponentially. Same with calcium chloride. Some of them are actually pretty dang linear, like lead nitrate here. It's pretty linear. Calcium chloride's pretty linear. Sodium chloride doesn't hardly appreciate, like, even after 100 degrees, it only went up like 6 grams in 100 grams of water, so it doesn't really go up that much. It does, but not quite. So you know, you can see that it affects some of these different. And then look at cesium sulfate down here. His solubility actually goes down as you increase temperature. So so this is kind of weird, you know, and this all has to do with the energetics of what's going on as these things mix and so on and so forth. All right, so you know, generally as temperature increases, your solubility increases, but it's not necessarily true all the time. For gases, the gases work different, okay, and the nice thing is for all gases, thank goodness, no exceptions, as temperature increases, solubility decreases. So essentially what we're saying is if we decrease the temperature, the solubility goes up. All right, so, and we've all experienced this if you've had soda, right? You pull a fresh soda out of the fridge, open it up, you know, and then you take a sip of it. It's nice and carbonated, fizzy and stuff. But if you take one that was sitting out and then you pop it open, you know, and you take a sip, but it's at room temperature, it's not going to be as fizzy because it's at a higher temperature, so the carbon dioxide has a lower solubility. Okay, and then you can also notice that even though they all decrease in solubility as we increase temperature, some of them decrease more than others, right? And the helium essentially remains unchanged here, okay? But like methane decreases quite a bit, okay? All right. So let's do some Henry's Law practice. Just one real quick. This is pretty easy. Okay, so it says calculate the concentration of CO2 in a soft drink that is bottled with a partial pressure of CO2 at 4 atmospheres over the liquid at 25 degrees Celsius. The Henry's Law constant for CO2 and water is this right here, 3.4 times 10 to the minus second molarity per atmospheres. All right, so we're calculating the concentration. So since we are sitting here, okay, and it's reached equilibrium, we can assume that our concentration is equal to our solubility. So Henry's law says the solubility of a gas is equal to the Henry's law constant times the partial pressure of that gas. In this case, it's CO2. So that means our solubility of our gas is equal to Henry's law constant, which is our 3.4 times 10 to the minus second molarity per atmosphere. Okay, and then our partial pressure of the gas is 4.0 atmospheres. Now, you can either memorize this formula, or really, if you just pay attention to your units, you notice that your atmospheres is down here and your atmospheres is up here. If we multiply these together, our atmospheres will cancel. We'll just be left with molarity, which is the concentration. All right, so if we take our solubility, so we take our 3.4 times, 3.4 times 10 to the negative fourth times 4, we end up with, did I screw this up? Oh, times 10 to the negative 2. Whoops. Here we go. 0.136, 2 sig figs, so it would be 0.14 molar. Nailed it. Cool. So that's Henry's law. Obviously, these get a lot more complicated. Like if our units for our pressure don't match with our K value, then we'd have to convert one of our pressure units. Okay, or we might actually have to you'd actually have to calculate the pressure, the partial pressure of the gas using something like Raoult's law, which we'll talk about in a couple of videos. Anyway, so let me know if you have any questions, and I'm pretty sure that's it. Let's just make sure. I'm pretty sure that's all I wanted to talk about. That's it. Okay, good. I'll see you on the flip side.